Okay, in this lecture we will complete our study of convex house. Recall that any algorithm for computing convex house on n points must take big O of n log n time in the worst case. We have proved it in the last lecture. And in the last lecture we have also seen a couple of algorithms which are poorer than optimal. The first one was big O of n cube running time. The second one was big O of n square running time in the worst case. So today we will see a couple of algorithms which are optimal. One is called Graham scan, and the second algorithm is named after its inventors, Preparata-Hong. Both these algorithms have a common thing. They have a pre-processing stage which nothing but sort the set S of points with respect to their x coordinates. Okay. So use any optimal sorting algorithm like merge sort or heap sort, and this preprocessing stage takes big O of n log n time by merge sort or heap sort. Okay, so in view of that, I will now assume my input is P1, P2, Pn, satisfying x coordinate of P1 less than x coordinate of P2 and so on. Fine. Now we are going to achieve a running time of n log n. So this preprocessing itself takes that much time, but that is no harm. If the rest of the algorithms also runs in this time, then you eventually get an n log n time algorithm that is an optimal algorithm for solving the convexal problems. And another thing you see, I am not assuming replicated x coordinates, so I have written less than instead of less than equal to. Okay, so it can be handled, equal x coordinates can be handled, but that you think of as an exercise. Okay, so now one by one, let us see how each of these algorithms works. I start with Graham scan. Okay. So since P1 is the coordinate with the smallest x coordinate, P1 is the point with the smallest x coordinate, it must be in the convex hull. This is the leftmost point, right? So suppose these points are sorted like this. Okay, let's say these are the points. So I will start, okay. First of all, Graham scan I will explain in terms of the computation of the upper hull. You can very analogously apply the algorithm to construct the lower hull. Okay. So I will construct only the upper hull. So this point must be there because it is the leftmost point. So I start with this, and to start with I will just join the next, the point with the next, the second x coordinate. Okay, second smallest x coordinate. Okay. So now what I will do, actually I am considering P1, P2, P3, P4, P5, P6, P7, P8, P9 in that order, in the sorted order. P1 should always be there. So this is P1, this is P2, P3, P4 and so on. Okay. Maybe I write it somewhere else, P4. Okay. So I start with P1, P2. Then when I consider P3, I introduce the concept of this, a left turn and a right turn. Suppose this is the last edge added. To start with, it is P1, P2. Later it may be somewhere else. Then I consider the next, this is the ith point. So I will consider P1, P2, P3, P4, Pi. So at this point, I have constructed the upper hull of the subcollection P1 through Pi. Okay. P1 is the leftmost point, and until this point, at this point, Pi is the rightmost point, so they must be in the hull. But later Pi may be thrown away. Okay. And the previous can be anything smaller than Pi, Pk. Some k less than equal to I minus 1. Okay. Now, consider this directed or oriented line, Pk, Pi. Okay. Then when I consider Pi plus 1, then if Pi plus 1 is somewhere here, then this is called a left turn, because you are moving here in this direction and then suddenly you move toward your left. Okay. On the other hand, if Pi plus 1 is here, then you are moving from Pk to Pi and then you made a right turn. So this case is called right turn. This is called a left turn. Now if you look at the hull, it's something like this. All turns must be right. Okay. So whenever you discover a left turn, this is caused by the previous point. So forget that previous point. So in this case, let us come to P3. This is a right turn. Here, here. Okay. So for the moment I keep it. Then I look at P4. Okay. And try to add it. But then I see that this is a left turn. Left turn is also the wrong turn. Okay, and right turn is right. Since this is a wrong turn, what I will do? I will simply delete this and connect this directly with P4. In this case, it turns out that P1, P2, P4 is a right turn. Therefore, I stop there, processing of P4 for the moment. Then what I do, I look at P5. This is once again a right turn. So I keep it for the moment. Then maybe I shift it slightly somewhere else. Okay. Then when I add P6, I see that this is a wrong turn. Is this. Okay. Then left turn, that is a wrong turn. So what I do, I simply replace this and this by this. Okay. Then I want to add this, and I see that this is a wrong turn, left turn. So I delete this and this and join this. But in this example, in terms of that, this is once again a wrong turn. Coming here, it goes a little up. Okay. So once again what I do, I remove this and this and connect it, sorry, it's not here, I connect it directly to this. This is P7. Fine. So it proceeds like that. So I can give you a pseudo code for this. More importantly, you see that the data structure that fits this context is nothing but a stack. Okay. You first start by pushing P1 and P2 to the stack. Okay. And then when you are considering Pi, there are certain things in the stack. So take the top two elements and then consider Pi, the last element you are considering. And if the previous points are P-prev and P-prev, just find out previous, and the current point Pi, whether this is a right turn or a wrong turn. If it is a right turn, then you simply push Pi to the top of the stack. If not, you remove the previous point from the stack. And once again, now the previous to previous point becomes the previous point. So you have, and previous to previous point now becomes previous to previous point. So once again, see whether that is a right turn and wrong turn. So this previous and this current point. If it is a right turn, now push Pi, otherwise that previous to previous point is also popped out of the stack. Keep on doing until either you discover a right turn or everything has gone out, all things are popped out, only the leftmost point remains. Only one point remains. If that is the case, then you simply push the ith point that you are considering in this current iteration. Okay. So I will write it this way. So let us give a name to the stack. Since I have used S for the input set, let us call the stack T. Okay. So T is my stack. T is initially empty. You start by pushing P1 to the top of the stack, to the empty stack. Then for I equal to 2, 3 up to n, you repeat. Okay. If size of T, let me write it this way, is 1, push, or maybe why do I treat it separately? Maybe I write this way. While size is greater than 1 and I say P previous, P previous, P I, is a wrong turn. So this means this is currently sitting at the top of the stack and this is just below whatever is on the top of the stack. So as long as you keep on detecting wrong turns, you pop P3. Okay, so in the next iteration this becomes PP and the previous point, if any, will be PP, previous. So you keep on doing this until you have discovered a right turn or the stack contains only one element. Okay. So this loop is broken when either this is a right turn or the size of the T stack becomes 1. Okay. Then you push okay, maybe I should also mention T here. Pop T from the stack T. So this is as simple as this. Okay. So I will come to the running time of this. Again, I will show you a better picture with the hope that it will make the exposition clearer. So I go here, Graham scan. Okay. Here. Okay. Yes. So these are my input points, 16 of them. P1, P2, P3, P4, P5, P6, P7, P8, P9, P10. Okay, so these are sorted with respect to their x coordinates. So at this point, we start with pushing P1 to the top of the stack. And at the stack contains nothing else, initially empty stack. Start by pushing P1. Then, you are trying to push P2. Okay. So this is straightforward because now the stack contains only one element. So you simply push P2. Okay. So the stack now becomes P1, P2. Okay. Then you consider P3 and you see that now this is the top of the stack. This is the just the element before the top of the stack, below the top of the stack. So now you see that this angle is, or this turn is right. So P3, let it stay. And the stack becomes P1, P2, P3. You have just pushed P3. In the next iteration, you handle P4. Do it. Okay. And once again you see that this is a right turn. So P1, P2, P3, P4. Stack remains like that. Now when you consider P5, okay, you now see the P4 is at the top of the stack, P3 is just below it. This is now a wrong turn. So I have to pop P4 out of the stack. And this becomes, stack becomes P1, P2, P3. I have not yet pushed P5. P1, P2, P3. Okay. P1, P2, P3. Once again, now P3 is at the top of the stack. P2 is just below it. And I once again check that P2, P3, P5 is a wrong turn. So I again throw away P3 from the top of the stack. So the stack now becomes P1, P2. And then I discovered that P1, P2, P5 is a right turn and therefore I simply stop by pushing P5 to the top of the stack. This iteration involves discarding P4 and P3 from the top of the stack and inserting P5 to the top of the stack. Let me see whether there are any other iterations. This one. P6, again, this is not a problem. This is a right turn. So, let P6 stay. And then P7. This is once again a wrong turn. So, what I do, I pop P6. This is once again a wrong turn. So, I pop P5. And now I see P1, P2, P7 is a right turn. So P7 is pushed to the stack. And the stack now holds P1, P2, P7. Clear? Okay, and this keeps on doing. Eventually you come to P16, the rightmost point. Whatever remains in the stack from bottom to top is now a clockwise listing of the vertices of the upper hull. For the lower hull, you can do similar thing, proceeding this direction, but this time you have to reverse the notion of wrong and right turns. Now left turn becomes right, right turn becomes wrong. Okay. Or for that matter, you can start from P16 and build the hull in the descending order of the x coordinates. So P16 to P14, P14 to P15 and so on. Then you keep your notion of right and wrong turns the same as the upper hull construction. Okay. Fine. I hope the algorithm is clear. Let me analyze its complexity a little bit critically. Okay, so I once again switch to blackboard mode. Good. Okay, so what is the running time of Graham scan? I will not deduce, but you see that essential operations are push, and each push may be preceded by a multi-pop operation. It's as many times as this loop is executed. It's pop, 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 multi-pop. And I think you have already seen in Edgy's notes that a stack which supports push pop, if you make a total of n push operations, then although this loop may be very costly, for some iteration it may be as big theta of n pops, but this cannot happen always, right? We have pushed n points. Okay. So at most n minus 2 pops are possible. You have to have the leftmost point and the rightmost point. So at most, I mean, if you consider total effort associated with these pop operations, okay, it has to be at most n minus 2. It cannot be bigger than that, right? And here you are considering what? You are looking at the top, the element just below the top, and you are computing a side. Left, right is nothing but, a side computation, right? Side, this. Okay. So, looking at these two top elements, this is O1 time, whether a computation of this wrong turn or computation of this turn, side PP, and PI, that is constant time, and pop is also constant time. So, the total effort associated with this inner loop is, it is never executed more than n minus 2 times. In the worst case, it runs. So, this total effort of this is big O of n. And there are n pushes, which is also big O of n. In fact, this is a way of, I would say, arguing that the running time is big O of n. But you have also seen that a stack supporting this and this, its amortized running time is big O of n, big O of 1 per iteration. Okay. So, you can view this in many ways. For example, the argument that I gave, this is also valid. So, total max n minus 2 iterations, not for each I, for all I. This way you can view it, or you can do a kind of amortized analysis. For example, if you want to use the potential method, you take the potential of the stack to be the number of elements in it. So you start with 0. Eventually, how many edges or corners you have on the upper hull, that will be your final potential. And since your final potential is greater than or equal to 0, this amortized analysis will show that the running time is big O of n. Okay. Fine. So, Graham scan has two parts, a pre-processing O n log n and the scan actually, which has amortized running time of big O of n. So, this part is actually cheaper than the initial pre-processing stage. You can actually compute the upper hull, or for that matter the entire hull, upper hull and lower hull together in linear time. But you cannot avoid this n log n time if you sort it. Okay. So this is very important. Graham scan actually runs in linear time after the pre-processing. But the total time is the pre-processing time plus this scan time. So this is n log n. Okay, so remember that this Graham scan, the scan part actually runs in linear time. We will once again require this result during when we study Voronoi diagrams. Okay. So this is pre-processing, this is the actual scan, total time is anyway dominated by the pre-processing time and it is n log n. And therefore, this is an optimal algorithm for computing convex hulls. Fine. I think that is fine, right? Okay. Anything else I need to say? I don't think so. This is a straightforward algorithm and it is illustrated with examples. Its running time is also interesting. Anyway, fine. So that's all about Graham scan. This is an optimal algorithm. So now let us look at the divide and conquer algorithm. Of course, it is not that it is very necessary because we already have an optimal algorithm. But anyway, let us see. It's an interesting algorithm. Anyway. So this is Preparata-Hong algorithm. So this is very much similar to merge sort. Once again I will assume that the pre-processing is done, that is the points P1, P2, P3, P4, blah 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 have strictly in ascending or increasing x coordinates. Okay. So what I do, given P1, P2, like merge sort, I simply cut this half at the middle. Then this plus 1 up to Pn. Right. It's just a guillotine cut at the middle, at the center. Okay. Just I am using this floor or ceiling notation because n may be odd. Okay. And then like merge sort, what I do? I recursively compute the hull, convex hull, the complete convex hull of the left half and recursively compute the right of the hull of the right half. Okay. And when does recursion stop? Maybe when the number of points is very small, like 3, 4, 5, 6, wherever you want to stop. And for the small things, you can even use the naive hull algorithm. No problem actually. Any other algorithm you can use. Because these are constant size instances, so solving them anyway take constant time. Okay, so what do I have now from the recursive call? two hulls. This is called the left hull, LH, and this is called the right hull, RH, maybe of S. Okay. Now, somehow I have to stitch these two hulls into a single hull, which is the convex hull of S, the entire set of forms. Okay. Fine. So, one thing is clear, since the x coordinates appear in the strictly increasing order, this hull and this hull are horizontally separated. Okay, it's not like this. It has to be something like this, separated. Right. That is the reason I want this to be, my points to be sorted. Okay, so they are separated. Now, somehow I have to identify a point here and a point here. And if I connect these two, likewise somewhere here, maybe here and here, connect these two. Then, if I keep only this part, then this line or line segment of this edge, then this part and this part, or if you look at it, if you look at the clockwise direction, here, 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 here. Okay. That will be my final solution. So, and so you have to discard this part. This to this for this hull and this to this for this hull. And then this, after this cut and paste, I am done. I have computed the entire convex hull for the, or all the points P1 through Pn. Okay. So the question is, how do I identify these 2 points? In fact, this is called the upper tangent. And this is called the lower tangent. Okay, so as you can see, if I can compute the upper tangent, I can follow a very analogous procedure for computing the lower tangent. So I will restrict to the upper tangent only. Okay, given any hull, a line passing through, an oriented line passing through a corner is called an upper tangent if the entire convex hull is to its, this direction is right. Okay. Okay. So, this is called an upper tangent if all points on the hull are to the right. Likewise, you can define a lower tangent if all the points are to the left. Okay. Anyway, so upper tangent, it is called upper tangent if all points are, or points of the hull are to the right of the oriented line, this line. Okay. And then how do you know? How do you verify something is an upper tangent? Procedure is fairly straightforward. You do not have to check whether all of these points are to the right of it. You only pick the previous point and the next point. And if you see that this and these points are to the right of this oriented line segment, and once again it's a side computation. So, 2 side computation you make. If both cases say to the right, then you are done. Why? because this is a convex figure, it cannot be something like it is on this side and then it will go back there and once again come back. By convexity, it is impossible, right? Therefore, whether a line passing through a corner of the hull is a tangent or not can be computed by computing only two sides, two side computations. You do not need three sides or this entire thing. Therefore, given a line, you can identify whether it is an upper tangent, it is an upper tangent in constant time. Okay. So, this upper tangent is actually an upper tangent to this and this. So, it is better to call it a common upper tangent for both the hulls, left hull and the right hull. Likewise, this is a common lower tangent for both the hulls. And I need to identify the 2 points of contact defining this common upper tangent and 2 points of contact defining this lower tangent. How? Okay. So, this procedure is very interesting. So, this point if I call P and this point if I call Q, I will start a search from the leftmost point here, from the rightmost point here and to the initial value of P is the leftmost point of this left hull, rightmost point of this left hull, and initial value of Q is the leftmost point of the right hull. So, PQ is something like this. Okay. Then what I will try to do, I will move counterclockwise along this hull until this becomes a Q will stay fixed for the moment. So, until this becomes an upper tangent. Okay. Now, if at that point of time, now P slides along this, eventually comes here and becomes upper tangent. Okay. But now I see what is happening here. You see that currently Q is like this, so even now P has changed, this is still not an upper tangent. So, I will now start moving Q until, let us say, it becomes an upper tangent. So, this is a march in the clockwise direction along Q, along the right hull. Okay. So, once I reach the point of tangency, I see, now I look at again P. If this is a common upper tangent, there is an upper tangent achieved here, but here, now I see it is no longer a tangent. So, I will keep on moving this, okay, until it becomes an upper tangent. So, this process is repeated. Move P until it becomes upper tangent and to the left hull, and then you check whether that PQ is a common upper tangent. If not, move Q, again move P, again move Q, move P, move Q, until this finally becomes the common upper tangent. Right. So, a picture, yeah. Picture is always good. Okay, steel grams can. Oh, sorry. Yeah, Preparata-Hong. Okay, so this is what I have already mentioned. This left hull, this is the right hull, and this is the common upper tangent, and this is the common lower tangent. I need to compute this. Okay. Okay. So, I start with this initial position. This is the rightmost point of the left hull and this is the leftmost point of the right hull. Okay. Now, I see whether this is a common upper tangent. Actually, you see that in this case, it is an upper tangent for the right hull. It is also a tangent, but it is a lower tangent to the left hull. It is not an upper tangent. Okay, you just extend it, it will go something like this. And everything is on one side, but it is the wrong side. It is a lower tangent, not an upper tangent. So I will start moving P along this. Okay, let us see what happens. Now you can clearly see it simply pierces through the hull, and therefore it is not an upper tangent. For the moment I will not look at this right hull. I will keep on continuing until this line becomes an upper tangent. So let me come here. It is still not an upper tangent because it pierces through it. So move P further. Now if you look at this is become an upper tangent. Okay. So I stop the march of P at this point, and then I look at Q. Is it an upper tangent? No. Now it just simply goes in the interior of this right hull. So I will now start moving this Q. Now, no. Now, eventually Q, this becomes an upper tangent. But once again you see, as soon as you have advanced Q, this has now lost tangency. Okay. So once again you move this, and now you see that this is an upper tangent to both the left hull and the right hull. And so you have found the points of tangency, this common points of tangency. And then you can throw away this. And there is another important thing that you see. This example actually illustrates. You look little carefully. This point is slightly above this point. Okay. So it is not necessary that during the march process you will stop at the topmost point here and the topmost point here. Definitely here it is the topmost point, but this algorithm says this is little below this. Okay. So your march did not end at the uppermost point. You may have to go further down, as this example illustrates. Okay. So I think that's a good example of merging two halves. Then let me once again switch to Blackboard mode, because I need to analyze the running time of this. Okay. So, good. So, what is the running time? Okay, so T of n is constant if n is small. This is the usual thing. It's constant for n, whatever base cases you use, 3, 4, 5, 6, it's always constant. Otherwise, like merge sort, you are creating two instances of size n by 2. Okay, and that's just a cut at the middle. That's apparently no effort with it. We go off one effort. Just its computation of n by 2. Nothing. Then, I need to consider what is the effort of merging two hulls. Okay. So, it is easy to see P makes only a journey like this. It never comes back. Likewise, Q starting from the leftmost point, it goes only like this. It never comes back. Okay. So, the total effort in each, I would say, stepping of P or Q involves a side calculation or two side calculations. Okay. To check whether it's an upper tangent or not, and then simply moving along the boundary of the hull. Constant time. Okay. So, how many times P can move and how many times Q can move? If I add them together, it cannot be bigger than n, because there are n points after all. right? Therefore, it follows that this runs in big O of n time. Okay, this march is always in one direction, this march is always in one direction, and before each stepping, you are making a constant number of constant amount of work, and there cannot be more than n stepping of P and Q together, because there are n points. Okay. Therefore, this running time looks very similar to that for merge sort, and the solution is therefore also identical. It is big O of n log n. That's it. So, of course, now this recursive procedure's running time is big O of n log n, not big O of n. Preprocessing also takes big O of n log n, but overall you get a running time of big O of n log n. Okay, preprocessing is also big O of n. Preprocessing is big O of n log n. And this recursive procedure is also big O of n log n. So, the overall running time, overall complexity is big O of n log n. Okay. So, this is yet another optimal algorithm for computing convex halves. Okay. So, good. One thing I would like you to investigate as an exercise. The correctness of the merging procedure. So, what is there to prove? Let us say this is the common tangent. Okay, common upper tangent. P moves from here, rightmost point, Q moves from here, leftmost point. Then, what you have to prove is that in this movement from here to here and here to here, first this, then this, first then this, then this. Okay. You never overshoot the common point of the tangency. That is, P never comes here. Q never comes here. Okay. If that thing happens, then this is not a algorithm. You keep on searching, once again you come back without ever being able to find the upper tangent. So, prove PQ never overshoot the think about this. Once again, you have to use convexity. It's not difficult. It's intuitive, but for formal proof requires some argument, and you have to use convexity. Okay. So, fine. So, we have proved, or I would say we have seen a couple of optimal algorithms for the convex hull problem. So, I believe that is good enough. In the next lecture, we will start an important thing called sweep paradigms. Okay. Fine. I think we stop here. Okay. That's all. See you. Bye.